Hey, fellow mathers! Welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim Montague, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we're on a mission to improve math teaching.
We know that algorithms are amazing achievements, but they're not good teaching tools because, y'all, mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop. That was me, by the way. I got trapped.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
We invite you to join us to make math more figure-outable. All right, Kimberly.
Yes.
You're supposed to say Pamela.
Pamela. I do say that a lot.
You do. Yeah. Sometimes it's when you're frustrated with me, Pamela. I think
it's my exasperated tone.
I think most often it's when you're like, Pamela.
Yeah.
Yeah. A little bit.
Like when I greet you somehow.
Yeah.
I don't see you as much anymore.
Yeah. Usually you say hola. Hola.
Hola.
Hola. Hola, Pamela.
Yeah.
There you go. All right. You guys know way too much about Kim and me. There you go. All right, Kim.
Tara Deanne sent us a review. Yeah. And the title is so cute. It said, I needed this in my life.
Aww. Thanks, Tara Deanne.
Yeah. She says, I love this podcast and have already felt a change.
And 5 stars I'm seeing.
Yeah.
5 stars. Thanks, Tara Deanne. Okay, sorry. Keep going.
I love this podcast and have already felt a change in my math teaching. Oh. Pam and Kim break it down in real-world situations and cover topics K-12. I suggest to anyone just finding the podcast to start at episode 156, literally called Start Here. Pam and Kim, you're amazing, and you make my Tuesdays brighter.
Oh, so our Start Here worked. That's awesome. Yeah. Nice.
Yeah.
Nice.
Start Here is a great episode for people who haven't really spent a lot of time in the podcast because it gives them some kind of underpinnings of the Math is Figure-Outable movement.
Okay. 156. 156, y'all. Check it out.
Yeah.
And maybe that's the one to pass on to your favorite person who you're trying to get to listen to the podcast.
Mm-hmm.
Tell them to start at 156. In fact, if you're starting listening to this podcast with today's episode, you might consider backing up a couple of episodes because we are in the 5th of a series that we are doing on exponent relationships, and we're kind of building off of what we've done before. So highly recommend that you check out the 4 episodes that have come before this to really get the most out of today's episode with exponent relationships. Kim, we're going to have some fun today. So sit up tall, take a deep breath, grab your pencil.
Yes, I have it.
I have my pen in my hand right now. Are you ready?
Yep.
Okay. Today's problem string, I'm going to actually tell you what the first problem looks like before I say it. Okay.
Okay.
So what it looks like is 2 divided by, but the divided by is a fraction bar. So 2 fraction bar, sort of not mathematical, but over. It's going to look like over. So 2 big fraction bar, and then 2 times 2 times 2. And we just want to simplify this expression.
Okay.
Which really means we kind of want to divide out any common factors.
Okay.
So simplify can often mean different things. Today it means to divide out any common factors. All right. So what are you thinking about? Maybe if you could tell us what you're thinking about instead of just the answer, that'd be great.
Yeah. So there's a 2 divided by 2 because there's 1 in the numerator and I used 1 of the 2's in the denominator. So I actually wrote 1 divided by 2 squared.
That's your sort of answer. 1 divided by 2
I wrote
squared.
2 things, but that's one of the things I wrote.
Okay. So I'm going to kind of try to write out what you said. I heard you say that there was 1 2 in the numerator and there was a 2 in the denominator. So I'm going to write 2 divided by 2. But then you had some leftover stuff. So then I wrote the times symbol with the dot. And next to that, I wrote 1 divided by 2 times 2. So that first 2 divided by 2 divides to 1. 2 divided by 2 is 1 times. And then that's where I think you had your 1 divided by 2 squared. And 2 squared is
4.
4. So you could write that as 1 divided by 4. Cool. I'm super curious. Did you ever, as we were doing this, get to 0.25?
No.
It's not in my lesson plan.
Yeah, I know.
And I don't know that I would have thought about it, except I was talking to you. Did you think 25%? You're just such a percent girl
I
now.
totally stayed in fractions.
Okay, cool. We've got this 2 divided by 2 times 2 times 2 equaling 1/4. I might then say, could we write the original problem in terms of exponents?
Mm-hmm.
So that 2, I'm going to write as 2 to the first. And that 2 times 2 times 2 is 2 cubed.
Mm-hmm.
Okay, so now we've got 2 to the first divided by 2 cubed equals 1 divided by 2 squared. Because you said that earlier, and I'm just going to kind of pull that over so that kind of at the end of my thing here, I've got 2 to the first divided by 2 cubed equals 1 divided by 2 squared.
Mm-hmm.
And then to make sense of all the things, last week we talked about how when you're dividing, we really want to kind of think, if I've got a bunch of the same base multiplied together in the numerator and a bunch of the same base multiplied together in the denominator, where do we have the extras? Because they sort of divide each other out.
Mm-hmm.
This 2 divides out that 2 to 1. This 2 divides out that 2 to 1. In this case, we just had 1, 2 divided out another 2. But if you have 2 to the first divided by 2 cubed, where do you have the extras?
In the denominator.
In the denominator. So today we've got 1 divided by 2 squared, and we're kind of, there's the first problem. All right, next problem. How about 3 squared divided by 3 cubed?
That's 3 times 3 in the numerator and 3 times 3 times 3 in the denominator. So then when I divide those out, I have 1 3 in the denominator. So I wrote 1/3.
1/3. That makes a lot of sense. Sure. With that 1/3, that's 1 divided by 3. Can I put an exponent of 1 on that 3? So it's sort of like 1 divided by 3 to the first power.
Sure.
I mean, it's not maybe necessary, but I'm just going to stick it there anyway.
Okay.
Because if we have any number just sitting there, it is to the first power.
Okay.
Okay, cool. Next problem. How about 5 to the 5th divided by 5 cubed? Actually, I meant to do one more thing. Sorry. Can we go back to the 3 squared divided by 3 cubed?
Mm-hmm.
I love how you wrote out the factors. What if you multiplied it out? What if you multiplied 3 squared out? 3 squared
27.
is
3 squared, so it'd be 9/27.
9/27. And is 9/27 also 1/3?
Yeah.
Okay, cool. Just wanted to do that as well. Okay, so now we're at 5 to the 5th divided by 5 cubed. What are you thinking?
I think that's 25 because I have 2 extra 5s multiplied in the numerator.
Cool. So we could write out 5 times 5 times 5 times 5 times 5 in the numerator, 5 5s in the numerator, divided by 3 of those 5s multiplied together in the denominator. And then we could line those up. And you're saying that you would have 2 leftover 5s in the numerator multiplied together.
Yeah.
So that's like 5 squared. So on my paper, I have all that written, but I might now kind of pull attention to the 5 to the 5th divided by 5 cubed equals 5 squared.
Mm-hmm.
And I might say, hey, does anybody remember that from last time?
Mm-hmm.
So I think last time we talked about this idea that where do I have leftover factors, and that we could sort of write that as that 5 squared as 5 to the 5 minus 3. 5 raised to the 5 minus 3 is 5 squared. Yeah.
Yep.
So with that in mind, now that we've kind of remembered that from when we've done this before, if we look back at the first problem, so the very first problem, we had 2 divided by 2 to the 3rd, or 2 to the first divided by 2 to the 3rd. Can we also write that as subtraction?
Mm-hmm.
As subtracting the exponents? Mm-hmm. Yeah, go ahead.
That'd be 2 to the negative 2.
What does that mean? And let me just be really clear what's on my board right now. So I've gone back to the first problem, and I'm focused on the last part. I have a series of equations, and I'm kind of almost might even circle this last part where I've got 2 to the first divided by all over fraction bar 2 to the 3rd equals 1 divided by 2 squared. And we landed on that when we did the first problem. Now I've got equals 2 to the negative 2 because we kind of did the 1 minus 3. So 2 raised to the negative 2. And now I'm going to step back and I'm going to go, what? And let kids just kind of absorb that a little bit. And then ask, what does 2 to the negative 2 mean? What does it mean to have a negative 2 exponent? And Kim, by Jove, kids will just go, well, it means exactly what we have there. It means it's 1 divided by 2 squared. Instead of us telling kids, we can actually do a lot of work to say, like, here it is. Make sense of that. And mathematicians had to do the exact same thing. Mathematicians had to go, could that work? Like, if we say that we can subtract exponents when we're dividing the bases, like bases, then we're going to get negative exponents. And does it, if that's true, will the rest of the math carry through? Can we continue to do things and that will actually work? And sure enough, it does. So now all of a sudden we've got some negative exponents to deal with. That's kind of interesting. Let's go to problem 2. Problem 2, we had 3 squared divided by 3 cubed, and we ended up with 1/3, or 1 divided by 3 to the first. Could we also write that as, what do you got, Kim?
3 to the negative 1.
3 to the negative 1. Sure enough. Cool. Next problem. How about 2 to the third divided by 2 to the fifth?
2 to the third divided by 2 to the fifth. Okay.
I'm going to take a drink while you think.
I've got 1 divided by 2 squared.
Why?
You said 2 to the third divided by 2 to the fifth?
Yeah. And I like your 1 divided by 2 squared, but can you tell
yeah, because there's 2 extra 2's multiplied together in the bottom.
In the denominator? Okay.
And so I'm going to put 1/4, but I'm also writing 2 to the negative 2.
Bam. And then we would want to let that sit and make sure kids are looking at it and feeling comfortable with it, and at least as comfortable as they can with it. Yeah, nice. How about if we were to go back to problem 1 one more time? I don't know if this is too crazy because we're on a podcast, but I'm going to try it anyway. Problem 1, we had 2 to the first divided by 2 cubed, and we ended up just a minute ago with 1 divided by 2 squared, or 2 to the negative 2. But we also said that was 1/4. Could we write that as 4 to the negative 1?
4 to the negative 1?
So 1/4. 1 divided by 4 to the 1.
1 divided by 4 to the 1. What did you ask if we could write it like?
I'm wondering if we can write that as 4 to the negative 1.
Yes.
That's weird, right?
Yeah.
Yeah, it's a little strange. But kind of cool. Notice that this is an opportunity where I could say, but did anybody actually do the math? Like, did anybody actually do the 2 cubed? What is 2 cubed?
4.
Cubed. 2 cubed. 2 cubed.
Oh, 2 cubed. 8.
8. And then what is, so I just wrote 8 in the numerator. And what is 2 to the fifth? Let me actually do it. So 8 is 2 cubed. So times 2 is 16, is 2 to the fourth. So times 2 is 32. Is that right? 32?
So 8:30 seconds?
Yeah. So is 8:30 seconds also 1/4? Yeah. Okay. So we have the ability here to use the numbers to kind of like play out. Is this actually tracking the way that we're thinking about all these guys? Cool.
And this is a little bit like you're attaching the way things are recorded to an experience that they're having.
Yeah. Yes, that is the attempt. Yeah. The attempt is to have the experience with the numbers and what they've been learning with exponents, and then saying, all right, with what you're doing, check it out. We can write it this way. When your brain does that, it can look like this. When your brain does that, it can look like this negative exponent. Super weird. We said last time that we could subtract exponents. Yeah, but that made sense because we had more in the numerator than in the denominator. So we just had a bunch left over in the numerator. Well, today we're having more in the denominator, more factors in the denominators of the same base than we have in the numerator. So we can leave them in the denominator. Or weird, if we can do this subtracting exponent thing, we can do the subtracting exponent thing and get negative exponents. What? What does that mean? Well, when we have a base in the denominator, we can we can write it in the numerator with a negative exponent. And that's crazy. It's a little interesting.
Mm-hmm.
Let's see if we can make sense of that in a problem that kids might run into. Like, what's 5 squared times 2 squared, all divided by 10 cubed?
Mm-hmm. So in the numerator, you have 5 times 5 times 2 times 2.
So I've just written that down. 5 times 5 times 2 times 2 divided by
10 times 10 times 10.
Okay.
But when you pair up a 5 and 2 in the numerator, you have 2 tens in the numerator. And
times each other.
And then 3 tens times each other in the denominator.
So I've just written 10 times 10 in the numerator and 10 times 10 times 10 again in the denominator.
Mm-hmm. So you have 1/10 or 10 to the negative 1.
10 to the negative 1. Da, da, da. That is a way that we could do that, and that's probably enough for our purposes today. I'm thinking. The other thing we could do is do the number thing, like we've kind of talked about. Number thing, like actually multiply things out. Is there a way that you would want to multiply out the 5 squared times 2 squared? Do you want to just kind of do it like it said? Or do you mind if I just do it like it said?
Yeah, go ahead.
So I might find a kid who said, yeah, 5 squared is 25 and 2 squared is 4. So in the numerator, I've got 25 times 4. That's just 100. So I've got 100 in the numerator. And then 10 cubed, that's 10 times 10 is 100, times 10 is 1,000. So I've got 100 in the numerator and 1,000 in the denominator. 100 divided by 1,000, is that just 1/10? Sure enough. Mm-hmm. It's like be another way of thinking about that. Or like you said, 10 to the 1. One other way that we could, as I'm looking at what we have here, when you said that you had 10 times 10 in the numerator, could we write that as 10 squared? Mm-hmm. And then 10 times 10 times 10 in the denominator was 10 cubed. Mm-hmm. So we've got 10 squared in the numerator, 10 cubed in the denominator. There's another way that we're looking at 1 divided by 10 to the first. Mm-hmm. Or that 10 squared divided by 10 cubed, that 2 minus 3, we're looking at 10 to the negative 1 in a different way.
Yeah.
So lots of different ways that we can kind of come at. Sure enough, we could, and y'all, I really want to impress that nowhere in here have we said, oh, and then that's the answer. In a big way, what we've done is we found lots of equivalent expressions. Mm-hmm. That's a big deal. So high school teachers, I invite you to consider that we have often said there is a correct answer, when really what we've meant is write the expression with only positive exponents. Mm-hmm. Or write the expression with nothing in the denominator. Mm-hmm. And I think we have to be, I'm going to invite us to be more clear on that. Let's be more clear on what we actually mean. Because the last thing I think we want is for kids to do the math correctly, get a correct equivalent expression, but because they didn't write it in the form that you meant when you said simplify or when you said do it or whatever, then they're getting marked wrong. Mm-hmm. We never want to mark wrong a correct equivalent expression just because we didn't guess at the one that you meant.
Right.
Yeah. So let's keep equivalence meaning equivalence. Okay, so I might end this problem string with a couple more generalizing problems. So I might say something like, what is 2 to the A divided by 2 to the B? And I've written that as in that big fraction form. So 2 to the A, fraction bar, 2 to the B. Kim, how are you thinking about that right now?
I think it's the same as it was a string or two ago. It's still 2 to the A minus B.
Okay.
But now we've added to our experience that maybe B is bigger.
That there's more 2's in the denominator than in the numerator. Yeah, sure enough. So is it could we also say that we're looking at a bunch of 2's multiplied together in the numerator, and there are A of them, and there are a bunch of 2's multiplied in the denominator, there's B of them, and they're where they line up and divide out to 1, we're gonna have some left over, and we're not sure where, but it's gonna be the difference between the 2's in the how do I say that? The number of 2's in the numerator and the number of 2's in the denominator. Wherever they're left over, they're going to be either a bunch left over in the numerator or a bunch left over in the denominator. If they're left over in the denominator, we can also write that as a negative exponent. Cool.
Yep.
Then we could have a similar conversation with M raised to the A divided by M raised to the B. So the same base M raised to the A divided by m to the b, and we can have the same conversation about we're going to have a m's multiplied together divided by b m's multiplied together. And really, we're just kind of curious, where do we have the leftover m's?
Mm-hmm.
And if the leftover m's are all in the, after we divide it out, if the leftover m's are all in the denominator, then we could potentially have, not potentially, we would have a negative exponent.
Yeah.
Okay. And so then lastly, to wrap up, I might say, then what does m to the negative a mean? And I'm kind of switching, and maybe I should have switched variables and done something like n to the negative p. I don't know, whatever.
Okay. Yeah.
In fact, let's do just, we're on a podcast. What is n to the negative p? Like, what does that mean?
It means that when I was multiplying n's in the numerator and more n's multiplied together in the denominator, I had more in the denominator. However many p times there were.
Pn's, right? Yeah, I had that many n's left over.
In the denominator.
In the denominator. So I could say, yeah, it's like, that's like 1 divided by n to the p, because I've got p of those n's being multiplied in the denominator. So n to the negative p equals 1 divided by n to the p. Cool. So here's a problem string where we're giving, for starting with numbers and looking at the relationships and making sense, finding all these equivalencies, different ways of writing these representations, and ending with a fairly abstract way of thinking about, so what does it mean to have n raised to the negative p? What does it mean that we have some base raised to a negative exponent? And bam, we can kind of reason about that, make sense of it, and use it to create equivalent problems. Does it make sense that we can use numbers to help students have experiences so they can generalize relationships, so that then when they see the generalized relationship, they can attach it to numbers, but not just so that then they can just do rules without thinking about it, but because they've developed a schema, they can then use that to help continue. They can use that to do bigger things, but also get inside that schema when they need to.
Yeah.
That would be an ideal place to go.
So this sequence of 5 tasks, what grade are you thinking?
Yeah, so I think you could start the first task that we did in this sequence, so 5 episodes ago. I think you could do starting in 3rd grade, definitely in 4th grade and 5th grade, to do the beginning part of it. 5th grade, especially the part where we get to the prime factorization part. 3rd, 4th, and 5th grade for the doubling and halving strategy. After that, I think as soon as you really want to kind of get into exponents and exponentiation and exponent notation. So typically that's around 8th grade. It's when you really start hitting exponent notation. Pythagorean theorem comes in typically in an 8th grade. Sometime I don't know all the state standards anymore, but typically it hits around 8th grade. And then from there, and I'm so glad you asked this. Let me just say, from there, so in 8th grade, you typically deal with exponents and exponentiation and solving Pythagorean theorem problems and that kind of thing, square roots. Then, so that then in an Algebra 1 class, you can do exponential functions. And my favorite way to do these exponent relationship problem strings that we've just done, this sequence of problem strings, is to do it interspersed while students are learning geometric sequences to begin with into exponential functions, so that I'm actually dealing with exponent relationships and exponential functions and exponential data at the same time. That we're sort of building everything. So you might be like, Pam, what are you going to do? These 5 problem strings in a row? No, actually, kind of, but I would intersperse them while I'm also building geometric sequences into exponential functions. So for me, this series of tasks could very much be in an Algebra 1 class or in an Algebra 2 class as we're trying to build exponential functions and grab the exponential relationships as we go. Yeah. Kind of cool.
Awesome.
All right, everybody. Thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable.